Okay.
This meeting is being recorded.
Okay, so let's go over the quiz answers here. Problem number 1. Let H1 and H2 be two hypothesis classes with H2 a subset of H1. And then it must be the case that the VC dimension of H1 is greater than or equal to the VC dimension of H2. This is a suspense true statements. That when we have this subset relationship, H2 here being smaller than H1, then H1, whatever hypothesis is inside of H2, is also contained inside of H1. And so anything that H2 can shatter, whatever hypotheses are used to shatter the data set that H2 can shatter, H1 will also have those hypotheses, and H1 will also be able to shatter those exact same things, but it's also possibly the case that H1 will be able to shatter more things. In your practice quiz, I gave you the opposite relationship, which is not true. It is not the case that DVC of H1 greater than DVC of H2. It is not the case that that implies that H2 is a subset of H1, but the other direction, the direction that this quiz is asking, is true. Especially as we get into more examples of various different hypothesis classes and doing interesting things with them, it'll be important to be able to differentiate between these two statements and know which one's true and which one's false. Problem number 2 here, let H1 and H2 be two hypothesis classes where the VC dimension of H1 is bigger than H2. Then if H1 can shatter some data set X, it is guaranteed that H2 will also be able to shatter that same data set. This one is false. And it's false no matter which direction this equality is going. I think I had originally intended it to be the smaller thing guaranteed to shatter the larger thing. But either way, just because even if these VC dimensions are equal to each other, it does not guarantee that some data set, the same data set, is able to be shattered by both of these hypothesis classes. Because the VC dimension is only about there exists some data set that can be shattered, not that all data sets can be shattered. So it's only the important thing here about the VC dimension is that just if there is some data set that can be shattered, then then the VC dimension is at least that size. So this one is false. Number 3, let H be a hypothesis class and X be a data set of size n. If H cannot shatter X, then the growth function of n must be strictly less than 2 to the n. It is the case that if the DVC is strictly less than n, that will imply that the growth function also is strictly less than 2 to the n. But just because there is one data set of size X, just because there is one data set of size X that we can shatter, or one data set X of size n that we can shatter, that we cannot shatter, that does not imply that the VC dimension is less than n. So X of size n not shattered. That does not imply that the VC dimension is less than n. There could be some other data set of size X that is some other data set of size n that could be shattered, and then our VC dimension would be at least n, and our growth function would be exponential in this case. So this is also false right here. Just because there's one data set of size n that we cannot shatter does not mean that our VC dimension is less than that size, does not mean that our growth function is non-exponential at that size, does not mean that our growth function is polynomial at that size. You have to be able to show that all data sets of size X, all data sets X of size n cannot be shattered in order to make claims on the growth function or the VC dimension. Question?
I have a question about that because to me it's kind of like the square root of the equal square in the previous question, but like, doesn't it have to be 2 to the n to be able to shatter any data set? Not even all, but just to be able to shatter a data set at all, it has to be 2 to the n?
So the growth function here, MH of n, is defined to be the size, the maximum size over all data sets. That word right there is data sets of the size of their dichotomies, h of x1 dot 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 xn. And this right here is going to be, that will be equal to 2 to the n if the data set is shattered. But because this is the max over all data sets, we only need one data set that gives us 2 to the n. Only one data set with 2 to the n dichotomies. Only one data set that can be shattered means that the max over all possible data sets is going to be 2 to the n. Because this is a max right here, many of these in real world problems in practice, many of these will not be equal to 2 to the n for real hypothesis classes. They will have to be something polynomial in n if it's less than 2 to the n. But many of these will be smaller. But we only care about the largest one of those. So we only need one data set to have the 2 to the n size for this max to be equal to 2 to the n. And for the max to be less than 2 to the n, it's not sufficient to show one data set is not shattered. You have to show that all data sets are not shattered to show that the max is not 2 to the n. Admittedly, a very subtle distinction here and a lot of words floating around in one big long string that all need to fit together in the right place. So easy to get confused here, have your miss some of the important key things there, but it's the fact that this is a max over all dichotomies is what means that just finding one data set that we can shatter is that we cannot shatter is not enough. This is related to when we are describing the size of the VC dimension. When we're talking about the size, when we're describing the size of the VC dimension, describing the DVC of a particular hypothesis class. We always do that in sort of two steps, providing a lower bound. The lower bound of the DVC being greater than or equal to something. This, in order to provide the lower bound, all you need to do is find one data set that is shattered. But in order to provide the upper bound on the VDC saying DVC is strictly less than something, this you need to say all data sets cannot be shattered. All data sets of whatever this size is right here, all data sets of that size cannot be shattered. This is many examples in this class of things that it's easy to sort of understand at one point and then totally not understand, and then feel like you totally understand and go back and forth between totally understanding, totally not understanding. This is one of those concepts that's, for me personally, when I was first learning this material, it took me a lot of going back and forth, feeling like I understood it, and then suddenly not understanding it at all. Just wrestling with it a bunch until it became comfortable. Which things are things that are like a for all statement, and which things are more a there exist statement. Last problem here, number 4. Define the hypothesis class of concentric circles as this thing. This was one of the hypothesis classes in the notes packet that you calculated the VC dimension for. And the VC dimension for this is just equal to 1 independent of the ambient dimension, independent of D. So this D right here does not affect the VC dimension. And so it does not determine like the size in any way of the largest data set that we can shatter. And the largest data set that we can shatter in this case is something of size 1. There is no data set of size 2 that this hypothesis class can shatter. And a breakpoint is a point, a size where we cannot shatter any data point of that size. So since DVC is 1, that is less than 5, we are guaranteed that 5 is going to be a breakpoint for this class right here. So this is true for number 4. Any questions about? Yes, Elliot.
Negative, so that it would match the hypothesis. Would that mean that the hypothesis class shatters a data set of size?
So I'll just work through why the VC dimension here is 1, and we'll argue that there is no data point of size 2 that we can shatter here. This is, again, one of the problems in notes packet 2 from chapter 2, one of the very first ones related to calculating the VC dimension. So here we'll start, again, whenever time we are calculating the VC dimension, we'll calculate the VC dimension right here, calculate DVC. We always divide it into 2 steps. First, the lower bound of showing that, in this case, I'm going to show that DVC is equal to 1. So for the lower bound, I need to show that the DVC is at least 1, greater than or equal to 1. And in order to do this, I need to show one data point, or show one data set of size n that can be shattered. And here, basically any point anywhere in the plane except possibly the origin is going to be able to be shattered. So the class of concentric circles looks like circles centered around the origin, where I believe it's putting pluses on the inside and minuses on the outside. So this hypothesis right here, we'll label this point as a negative. And if we were to instead use this green hypothesis that's a little bit larger, plus minus, we'll be putting a positive on this point and a negative outside. So we've shown that all possible labelings of this data set in red, which is just a single point, can occur. So this right here, that is the proof of this statement right here, showing that the data set of size n can be shattered, data set of size 1 can be shattered, and so we have provided this, shown this lower bound right here. And then in order to show that the DVC is less than 2, and this is what the actual question, getting to the actual question, the upper bound here, showing that the DVC strictly less than 2, we need to argue that for any possible 2 set of points, there is no way that we can shatter those 2 set of points. And so with these 2 points right here, it doesn't, yeah, well, I guess I'll first show why these 2 points as they are cannot be shattered, and then I'll argue why these 2 points are representative of all possible data sets. So first of all, if we use this pink hypothesis, magenta hypothesis class right here, we already talked about we're getting a negative on this point right here. We're also getting a negative on this point right here. If we go back to the green hypothesis class, now we're getting a positive on this close point right here, and we're getting a negative on this point right here. So that's 2 different labelings right here, positive, negative, and negative, negative, 2 different labelings. A third hypothesis, we'll use orange, and I won't complete the circle on this one, but looks like that with the circle going all the way around. Again, positives on the inside and negatives on the outside. And with this hypothesis right here, we get a positive right here and a negative right here. But it turns out that there is no possible way that you can draw a circle here that will cause this inner point to be negative and this outer point to be positive. So a negative, positive like this. There's no way for this blue labeling to happen. And the reason for that is because, again, these circles, the way the hypothesis class is constructed is that the inside of the circle is always positive and the outside of the circle is always negative. And so no matter where I draw this circle, whatever data point is closer is always going to be positive, and the point that's farther away is always going to be negative. And there's no place that I can put a circle that will switch that around. The reason that generalizes to all possible data points is because all possible data sets is because no matter where I put 2 points, I'm always going to have one point that's farther away from another point. And if one point is farther away from another point, then the close point will never be able to get the negative label with the far away point getting the positive label. So even if I were to adjust this data point right here and say place it way down here, moving this like this, it doesn't matter that the close data point, the thing that matters for this hypothesis class is just how far away you are from the origin. And this close data point is, there's always going to be one data point that's closer, and that data point that's closer can never have the negative label, while the far away data point has the positive label. So again, the shattering here, we talk about the hypothesis class doing the shattering and not a particular hypothesis doing the shattering. So it never makes sense to talk about a hypothesis doing a shattering, but here this hypothesis class of concentric circles cannot shatter any data set of size 2. And that shows that this upper bound right here, both of those two things together implies that the VC dimension is 1. I don't know if that somewhere in there, Angelina, answered your question or not. Other questions about this or anything else from the quiz? Okay. Number 3 on the quiz.
What really not clear was the distinction function. Just could you speak a little bit more to the relationship of like when the growth function is to the end, is still
Sure. I think I get the direction of the question. So there are many equivalent definitions of the VC dimension. One definition of the VC dimension is the largest n such that the growth function m sub h of n equals 2 to the n, equals this exponential value right here. And so here, when I was talking about if the DVC is less than n, well, the DVC is the largest value of n that the growth function is exponential. So if the DVC is strictly less than n, that does mean that the growth function must be strictly less than 2 to the n, because the VC dimension is the largest n where we are exponential. Another equivalent definition of the VC dimension, equivalent VC dimension definition. Equivalent definition is that it is the largest n where there exists some data set, there exists some data set of size n that can be shattered. And the key part about how this this problem sort of connecting these two definitions together, because we're talking about not being able to shatter one data set, and how does that impact the growth function. And in this case, because this definition says there exists some data set of size n that can be shattered, just because we found some data set of size n that cannot be shattered does not mean that there is not some other data set of size n that could be shattered. So the important thing here, the way that if people miss this, they probably made a mistake, is that instead of thinking about this in terms of there exists some data set, you're probably thinking about it like for all data sets. So it's important to keep track of where it's a for all and where it's a there exists in these definitions. Eva?
I was just going to ask if you were to reword the question.
Oh yeah, so the question is there a way that we could reword this question so it becomes true? And to reword this question to make it true, instead of having X be just like some particular data set of size n that H cannot shatter, we'd have to say H cannot shatter all data sets of size n. Then MH of n must be strictly less than 2 to the n, then that becomes a true statement. So I didn't use the words there exists here, but this is like sort of making that even more explicit by this is the there exists. I'm providing an explicit X right here. So when if you see me like providing some particular example, that's like a there exists sort of statement. So there exists some data set that cannot be shattered, but that's different than saying all data sets cannot be shattered.
So in this sense, is it basically, and same for the reverse on the 14 malpractice one, it says the HBA hypothesis class and X be a data set with endpoints if the growth function is equal to 2 to the n, then it must be the case that H is shadow X. Is it just basically like, unless you say all, there's always a, well, it might. Like, is that kind of how it is then? Because it kind of seems like, I don't know, it seems like it's kind of like, trying to be like, well, it could do one that we don't talk about. Like, is that kind of the case for both, Sean?
Your intuition there is correct, yeah. Yeah, so the DVC, the way that it was originally conceived and the way that most people think about it is that the DVC is like a worst case scenario for generalization. That it's worst case because there's some, there could be some data set that that we get that we're like maybe too powerful on that some data set that we can shatter that data set. So yes, there are other notions of complexity that we are not talking about that are not like this worst case notion of complexity, but the VC dimension is this this worst case notion of complexity. Yeah. Okay. All great questions. And again, yeah, very tricky, very subtle stuff going on right here. Today in class, we're going to do two things. First is that your next homework, programming homework, has been posted, so we'll talk a little bit about that. And then we will finish up going over this set of nonlinear transformations nodes. After today, we will have talked about everything, all the material for the midterm exam. And then again, next week is not your midterm is the week after that. Next week, I'll provide you the scheduling signups and we'll do some review stuff about the midterm and how to do interviews more generally. So first, talking about the homework assignment. So do, not this coming Sunday, but the Sunday after that. And this homework is similar in format to your previous homework, where I have a Jupyter notebook for you. It's got a lot of different stuff going on inside of it. This notebook is bigger than the previous one by probably like 3 or 4 times, quite a bit bigger. And spread throughout here are various questions that it's asking you to complete. So not just something at the very end, but there are parts throughout the middle, like right here where it's asking you to complete something in the middle of the notebook. And basically you'll just start from the top and work your way down. A couple things I want to highlight about this. So first of all, this is exploring, here I'm using the term half spaces and the polynomial kernel. The perceptron hypothesis class, often also called the class of half spaces. So everything that is in this homework assignment here is coming from this set of notes right here, just exploring this set of notes. And let's see, you'll do a handful of things. First, you'll just actually plot the VC dimensions in different regimes. Maybe one thing too I haven't said yet is that running this kernel, if you press, or running this notebook, if you click up here to run all cells, it'll take anywhere from like 10 to 30 minutes to run everything. There's a lot of computation going on in here. That'll generate a lot of these plots and run a lot of different models for you. The things that I wanted to, yes, let's zoom out a little bit again. One of the things that this has you exploring is looking at the shapes of the results of polynomial kernels. So here is an example data set where the polynomial kernel is in one dimension. And it's going to have you change some of these properties over here. P is what this notebook uses instead of Q for the dimensions. Yeah, P is a little bit more common in other literature, so it's what I use in my head, what I was using when I wrote this. The textbook, though, used Q, but P and Q, same thing here. Here, degree 1 looks like this. If we take it degree 2, we've seen an example of this in the pictures before. It lets us capture like circle-ish sort of shapes. But higher degree things, very hard to like really get a sense of what these higher degree things are capturing without seeing a lot of different pictures. So here's an example of a degree 3 sort of decision boundary that you can make, very not intuitive, like how this relates to third degree things. So the notebook has you playing around with that a little bit, experimenting with different noise values. And then there's a lot of plots that look something like this. And I want to talk a little bit about these plots. So these 3 plots right here are our training error, our testing error, and our generalization error. And I'm going to come over here to describe these plots in the abstract sense. So I'm going to redraw some plots that we've seen before. And you should, one of the purposes of this assignment is to actually like see the real world, how these plots actually are going to look in the real world. One of these plots is with in on the x-axis down here. This is everything from section part 3 is about plots with in on the x-axis. And the way we visualized this before was that as our in value increases, our in sample error, E in, is going to go up like this. And one of the things that you will see is that there will be a large section of 0 before things start increasing. This part right here is where the first breakpoint is going to be located. First breakpoint. One of the reasons why this is called a breakpoint is because the in-sample error is going to stop being 0 and start being larger than that. The 0 pattern breaks and the in-sample error starts increasing. And the reason why we're getting a 0, why En equals 0 right here, En equals 0 at this point, is because we are shattering all of the data sets that we're generating at the small n values. Shattering the data sets, and if you shatter the data set, then you have an En of 0. You'll also see in the plots that the out of sample error is going to be coming down as your number of data points increases. And the plots over here, these are all with what we call synthetic data. Synthetic data. Your last assignment was with the real world MNIST data. But synthetic data is data that like we are generating data that we generate. And because like we are actually generating it, it's possible for us to know, like, we know the F value, we know F, the true function, and we know whatever error measure, whatever noise is there, we know F and the noise. And so it's possible for us to actually just get the E out values. And let's see, the difference here between E out and E in, again, are generalization error. Generalization error. In the plots over here, the generalization error is always going to be on a log-log plot. So you'll have to be careful as you're looking at the plots that the training error, testing error, those are not on the y-axis here, not log plots. The x-axis for all of them on a log scale. But here, the generalization error on a log-log plot. You'll see that the generalization error will generally look like a straight line on all of the log-log plots with some weird aberrations just due to noise situations. And the last thing that this sort of plot talks about is this difference right here, what EN converges to as we get infinite data. This distance right here, called the approximation error. I mentioned this term just once when I drew this picture before, but so approximation error, or sometimes called the bias. This notebook will explore a little bit more about this approximation error. We'll talk more in detail about this approximation error after the midterm, and so you're not responsible for it in detail on the midterm, but it is helpful for understanding here in the pictures and the plots exactly what's going on. So this is the part 3 plots. It'll have a handful of things that you have to do related to plots looking like this. Then part 4 and 5 are related to the plots that we've seen a little bit more often. That looks something like, on the x-axis down here is our measure of model complexity. In part 4, that's going to be equal to the number of dimensions, which is equal to our DVC. In part 5, that will be our Q value, or the P value as it's written in the notebook, which has a complicated relationship with DVC. We said that, again, the DVC equals the Q plus D choose D, which is a little bit less intuitive. But again, the notebook will hopefully help get you some intuition for this right here. And the plots over here, the key way to visualize this, the thing that you need to remember is that start with the in-sample error first. As model complexity increases, the in-sample error will go down, but the generalization error, E in minus E out, going up. And the out of sample error, again, the thing that we actually care about, will look something like this. I've drawn this particular plot here, I don't know, like at least 3 or 4 times now in class. It's because it is like an extremely, extremely important plot. This is something that this relationship definitely need to have burned into your memory about how all of these different error measures relate to model complexity. Coming back over here, I want to scroll down to part 4 so we can see what some of those plots look like right here. So the generalization error, again, on this far right plot here is the generalization error, E in minus E out, and you can see that it is increasing in this logarithmic way right here. There's a log scale. The E in over here decreasing, and here you can see that it decreases until it gets to 0, until it hits this breakpoint, and now it is 0 everywhere after that. And this plot right here, this middle one, is our E out. This is the one that we care about. And it's a little bit hard to see how this plot right here, this middle plot, relates to the thing that I drew right here. This middle plot is this U-shaped right here. But there's you can see it's a little bit, you have to look close, but it's higher over here than in the middle. There's this middle over here, this middle being the optimal number of dimensions that we would have for our problem. We select our degree of our polynomial so that we hit this middle point right here. And then after we hit this point, the error starts shooting way up. It's very common for the plot of the true out of sample error to have a very sort of unbalanced kind of U shape like this, where one edge is much, much higher than the other. So commonly draw it like this to visualize it, where everything is equal. But it's very common for the shapes actually to not be equal to each other. The first 4 parts here mostly have you just running code that I have and visualizing it. The last part, part 5, you'll have to create that whole experiment from scratch for this Q value on the bottom side, for the degree of the polynomial on the bottom side. And you'll know you've done part 5 correctly because you'll get some sort of plot like this, where there will be some optimal Q value that'll be some moderate number, like between, say, like 3 to 5. And if your polynomial is too small, you'll get bad results because your in-sample error will be too large. And if your polynomial is too large, you'll get bad results because even though your in-sample error is small, your generalization error will be too large. So again, part 5, you know you did it right. Part 5. Did it right. If you get a plot that looks like this, possibly, again, it'll be a little bit unbalanced with the U not being a perfect U shape, but one side being higher than the other. And the middle point, the optimal E out, will be some sort of moderate polynomial size. Something like between, say, 3 and 6. Exact values could be different for different people because there's all these data sets are generated randomly, and your computer might generate different random numbers than other people's, but everybody should get a plot that looks something like this with your optimal values somewhere between 3 and 6, something like that. Yeah, I don't know that it makes too much sense to pause here for questions because you all haven't had a chance to look at the whole thing right here. But again, I'll say that just the computation alone on this takes about up to a half hour, depending on your computer, to run through it all. My laptop took about 20 minutes. And so could be a longer assignment just from having to wait for the computer to do stuff. Okay. I don't know. I guess I will pause for questions. Any questions about any of that, what to expect? Okay. Then we'll spend the rest of the class today finishing up this chapter 3.4, nonlinear transformations notes. And again, this will be the last material for your midterm exam. And the point of this programming assignment, this giant Jupyter notebook, is to help you see that the things that we're talking about mathematically here do actually correspond to what's happening in practice in the real world with different models. So as you all are pulling this up, one last thing that I'm going to highlight here. So this big section of code right here trains a whole bunch of different models. Inside of scikit-learn, there are 6 different hypotheses classes that implement the half spaces hypothesis class, the perceptron hypothesis class, and all 6 of these things have the same statistical properties. After the midterm, what we will be doing is we will be going into scikit-learn and talking very specifically about all of these different models implemented in scikit-learn. What are their hypothesis classes, and what does that tell us about how to use them and when to use them? But here, all 6 of these things, one thing that we know already is that they're all going to give us basically the same results because they all are the same hypothesis class. Okay, so chapter 3.4, nonlinear transformations. Last time we defined the feature transformation as this phi variable that you apply to your data set before passing it over to whatever model you're doing. And we talked about the most important of these generic feature transformations is this polynomial feature map. This allows us to increase the VC dimension. And then other 2 that we talked about are the PCA feature map and the random feature map. These allow us to decrease the VC dimension. The PCA and the random feature map, both examples of dimensionality reduction techniques. And the random feature map in particular, famous for being both very non-intuitive and very, very high performing. Got this 2017 Test of Time Award for being the most important algorithm developed in the early 2000s. And again, still state of the art today on many important real world applications. Today, we're going to start here with problem 3.4, talking about what is called the decision stump. So this problem 4 right here comes from example 3.15 in the textbook. And this is an example of a feature map that is often not implemented in practice as a feature map and often implemented as its own sort of separate hypothesis. But this is the hypothesis class of decision stumps. Looks like a feature map like this attached to a perceptron hypothesis class. And what this feature map is telling us is that X here is a vector. This bold X on the left-hand side is a vector. And this K right here is like this parameter to phi determines which one of the phis we're using. And the particular K value determines which entry inside of X we're going to care about. So if we have a 2-dimensional problem, like this, then what phi sub 1 would look like would be a bunch of, we only care about one dimension right here, and we select one particular linear decision boundary on that first dimension. All these blue lines are example visualizations of what our phi sub 1, h sub phi sub 1 looks like, where our new hypothesis space is only this dimension right here, and we're doing linear classification along that dimension. And then h2 or h sub phi 2 does linear classification along the other dimension. This is these decision stumps are very closely related to the h-axis and h-axis 2. To h-axis or h-axis 2. And h-axis and h-axis 2, the right way to think about them is that they are like the finite counterparts of this decision stump hypothesis class. And the decision stump is like a infinite generalization of h-axis and h-axis 2. For the finite h-axis and h-axis 2, we can only pick particular values here along the like a particular axis, and the line is located exactly on the axis, passes through the origin. But the generalization of the decision stump is that our line doesn't have to pass through the origin. It's still aligned with the axis, but we can move it somewhere along the axis. So that's the visual intuition of the decision stump here. Part 1 here of problem 4, state an upper bound on the VC dimension of H sub stump in terms of D using big O notation. So here the DVC is just equal to theta of log of the total number of dimensions. So this is a dimensionality reduction technique because we are reducing the dimensions by the log of D. That implies dimensionality reduction technique. And it reduces the dimensions by a lot. That anytime you're taking the log of something, that really reduces the size of things. So this is something to use if you really need to reduce the dimensions by a lot. Again, the other connection here to the h-axis and h-axis 2 is that, say for the m of h-axis, that was equal to d, and the dvc of h-axis was equal to the log base 2 of d, and so that's theta of log d. Same VC dimension for our continuous approximation or our continuous version of the decision stump here. Going from the h-axis to the decision stump it gives us more power in terms of what we can fit in our E in, but it does not like give us downsides on the generalization here. Let me write that out and then I'll stop for a question. So one thing that we know is that H stump is going to be a superset of H-axis. Also H-axis too. H stump is a superset of H-axis because H-axis, again, these lines have to be perfectly going through the origin along one of these axes. H stump gives us more flexibility, but so this will imply that the E in of whatever we select for our stump, so I'll say G stump, that is going to be less than or equal to our E in for G axis 2. So we're guaranteed to have our in-sample error be at least as good. And our generalization results over here, we have the same VC dimension up to constant factors. So we're basically going to get the same generalization. So the decision stumps are strictly better than our H-axis, H-axis 2 finite classifiers. Okay, I said a lot of things. Good. Stop to pause for questions.
Just a clarification.
Yeah.
For equation 5, what does the 1 indicate?
Equation.
Like you're taking a single value.
The question is this 1 right here. Why is there a 1 right here? The answer is that, let's see, we'll do this in, I haven't used orange. So our H hypothesis class, our perceptron hypothesis class looks like X into the sign of W transpose X like this with some other stuff right here. And we said before that, that this is really, there's been some sort of already feature transformation happened where we added a 1 onto our X, that this X here is like a modified actual data point where there was 1 comma X and our B comma W term, that the 1 over here was to account for allowing us to have a bias so that the thing, our separating hyperplane didn't have to go straight through the origin. And it was just for notational convenience that we keep writing it like this. And this one right here is the textbook. At this point, when they talk about the decision stump, they go back to including the one in their definition of the feature map right here. Other sources will not include the one right here and keep it implicit, kind of like it was implicit right over here.
So it's just bias.
So this is the bias term in the linear function over here. It is the offset from the origin. Yeah. You will also see this written though just as x sub k with that bias term sort of implicit in the notation, like it's implicit over here. Really good question, actually. A lot of things notation-wise. Again, I've highlighted a handful of things in the textbook here, notation-wise, that are maybe less than optimal. But machine learning people in general, pretty fast and loose with notation, assuming that the reader is able to keep up with weird notation changes like this going on. So you'll see this happen a lot in different sources, that the one's sometimes included, sometimes not included. So good questions. Other hands up. Arsh. Why is it theta log D and not O of log D? And your question here is for the blue here in the, for the decision stump, why did I put theta here? Let's see, so it is true right here what I've written about it being theta. The textbook, I don't remember the constants. They might just provide the upper bound of some constant like 2 log 3D, something like that, of what they say. It might be the case from what the textbook says. The only thing that we can know for sure is that it's an O, but it is true that it's a theta. Oh yeah, good question. Intuitively, why is there a lower bound on that? It has to be at least the log of D. I don't have a short explanation for that, other than anytime you have like D dimensions, there's a that you're selecting from. There's a like permutation effect going on that causes a log D factor here to appear. Anytime you're selecting from D things, you get a log D in your VC dimension. Anytime the VC dimension contains a log of something, it's probably because somehow you're selecting between this many choices. We will see some other things in the future that also have this, that also have some sort of like selected dimension kind of component going along with it. Yeah, so I guess the textbook does work through the derivation of showing this bound, at least the big O part of this bound. But the important thing here is the final result. Hopefully that sort of answers your question. All really good questions so far. Any other questions about the decision stumps? Okay, so for many dimensions but few data points, explain why using our VC theory. So if we have many dimensions, so our dVC again is proportional to whatever our dimensions are when using the perceptron hypothesis class. I'll write it using the theta notation equals theta of D. And if D is much, much larger than N, that implies also that the dVC much, much larger than N, which implies that our generalization error is going to be very high. The reason for that is because the generalization error is proportional to the square root of dVC divided by N. If dVC is much bigger than N, then the generalization error high, this thing on the numerator, this thing on the denominator. And so in order to make our generalization error much lower, We generally want our DVC. So good rule of thumb again. Rule of thumb is that the DVC should be approximately, or rather 10 times the DVC, 10 DVC approximately equal to N that we need about. Is a good starting place for doing something reasonable, having our number of data points be 10 times the amount of VC dimension. And so if we have way more dimensions than in here, way more dimensions than data points, then we need to reduce them somehow, and the decision stump's just one way of reducing them somehow. Let's see, moving on here. So single feature transformations. This problem 5 here, super important one. Very common situation here, what we're going to see. So many features are discrete. And then what that means is that they have a fixed number of values where the value has little semantic meaning in and of itself. There's a real world data set called the German credit data set. This is a data set that we have used in the FinTech practicum and the data science capstone, working with different banks as they're exploring their whether you should provide credit to somebody or not provide credit to somebody. So it is a common data set and wide use, and has very many of these discrete values. One of these values is their marital status value, and it has this rather awkward definition that it can either have a 1, 2, 3, 4, 5, or 6 as its value, and these values correspond to like totally random things about single, never married, married, first married, single, divorced, single, widowed, or if it's a 5 and 6, it even encodes the sex of the person somehow. So it's this weird thing that sometimes encodes like sex status, sometimes encodes whether somebody's been remarried or not remarried, has a lot of stuff going on inside of here. And if we were to use a perceptron classifier by itself on this, what we would have to do is we'd have to pick some like threshold basically in this system and decide that the things either below are good and above are bad, or vice versa, that the things below are bad and the things above are good. And in this case, that like makes absolutely no sense at all, because there's no relationship between like number 1 and 2 here and how they're like somehow closer together than 5 or 6. And so the common way to handle these sort of situations is called one-hot encoding. And what that does is instead of having one column with 6 different values inside of it, we would convert this into having 6 columns, each with just a 1 or a 0 inside of it. Each one of those columns corresponds to the 1, 2, 3, 4, 5, or 6 over here. If the original value is 4, then the new column 4 would be equal to 1, and all other columns equal to 0. Extremely popular, extremely common encoding thing to do. And this question's about how does that affect how does doing that affect our generalization here? So part 1 here, if the discrete column has C possible values, then the feature space, D tilde, anytime you see the tilde, the squiggle, that means that it is your feature dimension right here, is equal to D plus C minus 1. So C is our new columns that we've added, minus 1 because we have deleted the previous column. And so what is the new VC dimension? Our new DVC, our previous DVC was equal to D plus 1. Our DVC is always equal to whatever our feature dimensions here are plus 1 when we're using this perceptron hypothesis class. And here the D squiggle, D plus C minus 1. So the minus 1s cancel out, and we could just get D plus C. So however many column values we have, we are extending our VC dimension by that much. In a lot of cases, that's not a problem, but in some cases it is. So one common use of these discrete values is, for example, like what city is somebody born in? And there are millions of cities around the world. And so if we were to use a one-hot encoding for what cities people are born in, then our VC dimension is going to explode by a very large number. Our DVC will increase by C, which in this case is large. So the DVC goes up by a lot. And that implies that our generalization error will also go up by a lot. Our in-sample error very likely to go down by a lot, but our generalization error here going up by a lot. And so then part B, how can we fix this problem? Anytime when we have a large generalization error and a small in-sample error, the thing to do is to do dimensionality reduction. Dimensionality reduction. And we've seen 3 techniques now to do that, either the PCA or the random features. Random features, or that decision stump hypothesis class. And so we can chain these feature maps together, first doing the one-hot encoding and then following it by some other dimensionality reduction technique in order to get our final VC dimension to be in that sort of good range where our E out will be minimized. And again, the rule of thumb, in order to get our VC dimension to be about 1/10 of the number of data points that we have. I'm going to keep pushing through here so that we can talk about this problem right here in the last few minutes. This mean centering feature transformation, we've seen this feature transformation before in slightly different language when we were talking about the PLA, perceptron learning algorithm, and ways to potentially make it faster. But when we were talking about ways to make it faster, we did not think about how that might affect the statistical performance of the algorithm. And so this problem 6 right here is talking about the statistical performance of the algorithm. In this case, again, our VC dimension is going to be related to the size of our output space of d tilde right here, and we're not changing the size of the space in any way. We're just moving the data points around. So our new DVC stays the same. DVC stays the same as equal to d plus 1 or theta d. And so this implies that no effect on our generalization error. That means it's always a safe transformation to do, not going to hurt us statistically in any way. So when should we do this mean centering transformation? 2 possibilities. The first one that we talked about, again, a long time ago at the PLA, is that if it makes the learning faster, this was the only one of the 3 transformations that I gave you in the notes packet that resulted in the learning being faster for the PLA. But if it makes the learning faster, like if you're using the PLA, then it makes sense to use it. Or you can try and just see if the in-sample error is better. If EN is better after doing it, which it often is, then you know that the generalization error is going to be the same. So if EN is better, generalization error is the same. So that'll imply that E out will also be better. There's one more problem in this notes packet, and this problem right here. It's again revisiting a feature transformation that we saw from the perceptron learning algorithm. The arguments, though, are basically the same as right here, that everything stays the same. And so just use it if it happens to make things faster or better. That's where we'll stop for today, though. We're out of time. If you have anybody has questions about any of this, I'll stick around and get those answered. Again, on Monday, no quiz on Monday. There will be a quiz on Wednesday, no quiz on Monday. And we'll also do the midterm review stuff next week.